Right. Welcome to this inaugural lecture in the new online series, Theorems of the 21st Century. My name is Ruslan Devichak, and I'm Deputy Head of School of Computing and Mathematical Sciences at the University of Leicester. Mathematics is arguably the most significant achievement of the human mind, with its vast and rapidly expanding universe of abstract objects and relationship between them, which are usually presented in the form of theorems. Even though everybody studies mathematics at school and many go on to study it at universities, modern mathematics is effectively incomprehensible to a vast majority of people. Even professional mathematicians, with very few exceptions, have only limited knowledge of modern developments in branches of mathematics where they are not experts. And so it was particularly impressive when our colleague, Dr. Bogdan Grechuk, decided to take on the challenge of explaining modern mathematics in a more accessible form to a wider audience. In his books, Theorems of the 21st Century and Landscapes of the 21st Century Mathematics, he collected over 500 theorems published since 2001 and presented them in a more accessible manner. And today we are taking another step in making modern mathematics accessible to a wider audience by inviting prominent mathematicians whose theorems were included in Bogdan's books to present their theorems in the form of an online seminar, which will be recorded and also made available on YouTube and other online platforms. And now Dr. Bogdan Grechuk will present the format of the seminar and introduce our esteemed speaker for this inaugural online seminar.
Thank you, Ruslan. Welcome everyone to the first talk in the seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Usually the talks will last about 45 minutes, and then you will have time for questions and discussion. Please feel free to type your questions or comment at any time during the meeting chat. So meeting chat is always on, and you can type your questions at any time. So it is my great pleasure to introduce our first speaker, Professor Boaz Klartag from Weizmann Institute of Science in Israel. Professor Klartag is world-leading expert in high-dimensional geometry with a long track record of solving central open problems in the field. And in today's talk, he will present a significant breakthrough on the classical problem of sphere packing. So I'm now happy to hand over to our speaker.
Thank you very much, Bogdan, for this flattering introduction. I'm going to discuss indeed lattice packing of spheres in high dimensions. Just before I start, so there will be time for questions at the end of my lecture in 45 minutes. But if you have some question about the notation in the middle of the lecture, something is not clear, some little thing, please use the chat. Please write in the chat your question, and then Bogdan or someone else will tell me, and I'll try to answer it. It's in mathematics, if you miss one little definition, sometimes you can really miss a full lecture. It's really a waste. So please use the chat for questions about things which are not clear. Okay, so I'm going to discuss indeed lattice packings of spheres. Let me begin by telling you what's a sphere packing. So we work in Rn. Rn, n is the dimension of the space, so R2 is the plane, R3 is the three-dimensional space. A sphere packing in Rn for general parameter n is a collection of disjoint Euclidean balls, all of the same radius. Okay? If you want, you can think about balls of radius 1, just a collection of disjoint balls of radius 1. Now, mathematicians distinguish between closed set and open sets, and for us, that says that the balls do not contain a boundary. I mean, mathematicians say these are open sets, open Euclidean balls in R3 without their boundary. Okay, just a collection of disjoint balls of the same radius. This is a sphere packing in Rn. If the sphere packing is reasonable, then it has a density. What is the density of a sphere packing? The idea is to take this collection of balls and take a large box in Rn and measure what is the proportion of space of the box that is being occupied by the balls in the sphere packing. If the sphere packing is nice enough, then as you let the box tend to infinity, this proportion of space tends to a number which is called the density of the sphere packing. Okay, so for reasonable sphere packing, you have this parameter density. What is the proportion of space that they occupy? And the question that we will discuss today is what is the maximal density of a sphere packing in Rn? Okay, that's the question. And it is a separate question in each dimension. And let us begin by discussing the case n equals 2. So sphere packing in R2 if you want circle packing in the plane. And in this slide, I show you an example of a circle packing. It is colored in some arbitrary manner. The colors mean nothing, just for so to be nice for the eye. But we see these joint circles covering some portion of the plane. Now, the circle packing that I have in my mind is not just this partial circle packing of some region in the plane, but in my mind, I continue this circle packing definitely in all directions, so that we think about it as a periodic circle packing of the entire plane. Okay? And this periodic circle packing of the entire plane, this one is called, it's a famous packing, it is called the hexagonal circle packing. Why is it called the hexagonal circle packing? Because if you look at the centers of all the circles, you just draw a thick dot at the centers of all the circles. I think you see my mouse, so you can see these centers. Then these centers have a nice property. So each circle has 6 adjacent circles. And if you draw edges between the centers of these adjacent circles, you have a hexagon. And this is why it's called the hexagonal circle packing. Each circle has 6 immediate neighbors, and the centers form a hexagon. It is a classical fact in mathematics that this hexagonal circle packing has a maximal density, optimal density, which is pi over root of 12, which is roughly 91%. Okay, so roughly 91% of the plane is being covered by these circles in this circle packing. There are more things that you can, more properties of these circle packing that you can observe. For example, if you look at the centers of these circles, you can see very clear patterns. You can see lines, right? You see parallel lines, horizontal lines, and some kind of slanted lines that are also parallel. You can also see that there are holes between. So if you count this region of space, the holes, these little white regions, there are roughly twice as many holes as there are circles in this circle packing. And if you look at the let me go back to the centers, the center of these circles, it's a very rigid object, very regular object, which in mathematics called a lattice. What is a lattice in Rn or in the plane? So there is one particular example of a lattice, which is called Z to the n or Z2. Okay, if you want, let me show you my way to the big Z2. These are all vectors in the plane with integer coordinates. This is Z2. And if you take Z2 and apply the linear map, the invertible linear map, then the shape that the collection of points you plane is called a lattice. So for example, in this case, you can apply a shear transformation. What's a shear transformation? You can take linear transformations that keeps the x-axis, okay, but it moves parallel lines with the x-axis, say to the right, at the rate which is proportional to the distance from the x-axis, and you can get what's called the hexagonal lattice, okay? So each lattice is a linear image of Z to the n. That this is a lattice. A lattice has an important parameter, important invariant, we say, which is called its covolume. The covolume is, okay, if you are familiar with the concept of a lattice, the covolume is the volume of the fundamental cell. If you are not familiar, the covolume of the lattice is the determinant of this linear transformation, absolute value of the determinant of this linear transformation. The linear transformation T is not determined by the lattice. There are many linear transformations that give you the same lattice. If you take, I don't know, I mean, some 2x2 matrix, I don't know, let's say 3, 4, 5, 3, it would give you, no, 3, 2, 4, 3, sorry. 3, 2, 4, 3, the determinant is 1. So it will, the image of Z2 under this any integer matrix of determinant 1 will give you still Z to the 2. It will give you exactly the same lattice. So the linear map T is not determined, but the determinant of T is the absolute value is determined. So this is an important parameter of the lattice itself, which is called its co-volume. And it's roughly the density of the points. If you take a large box in the plane, and if the box has a volume R, then you roughly expect to see R over the co-volume lattice points in this box. Okay, so this is the proportion of lattice points that you have in the plane. Pretty much you have one, if the co-volume is R, or co-volume, let's call it X, then you have one lattice point per volume X. It's the fundamental set. That's the co-volume of a lattice. Okay, so why do I have this fix? Why do I elaborate about lattices? So what's the relation between field packing and lattices? So as it turns out, lattice field packings are particularly important. So what is a lattice field packing? A lattice field packing is first of all a field packing. So it's a collection of disjoint Euclidean balls, all of the same radius. But I add one requirement. I require that the centers of these balls would form a lattice in Rn. Okay, so this like in this example of the hexagonal circle packing, the centers are a lattice. It's an image of 0 to 2 under linear map. I require this is a lattice field packing. And why do we care so much about lattice field packing? Because of the following empirical, because of the following fact. So there are very few only very few dimensions where we know the exact optimal density of a field packing. And in any dimension where we know what the optimal density is, there is a lattice field packing attaining the optimum. Okay, so these are dimensions 3, 8, and 24. Okay, so let me now tell you a bit about the field packing problem in dimensions which are not two. Dimension, let's move on to dimension 3. Okay, we like dimension 3 for obvious reasons. So in dimension 3, it is known that the optimal density of a field packing is pi over root of 18, roughly 74%. So you may cover space, roughly 74% of space by these disjoint balls. And as I said, the optimal density is attained by a lattice field packing. And what is this lattice? So actually it's nice because there are two lattices, two different lattices, distinct, not just one. One is not rotation of the other or not a reflection. They're really distinct lattices that attain the optimum. And scientists call them FCC and HCP. Okay, and there are various materials in nature whose atoms are locally arranged according to one of these lattices. And you can see in the list I wrote on my slide that so some materials here, some materials there. There is a material called cobalt, which appears in both lists because at some temperatures, I think up to like 400 Celsius around, the atoms are HCP, according to one of these lattices. And then if you warm it up, then it remains solid, but the atoms kind of switch to the other arrangement of the optimal arrangement while preserving the volume because it has the same density. Let me try to explain to you how to construct these two lattices, okay? FCC and HCP. So there are layers of balls, of oranges if you want. Each layer is just the hexagonal circle packing. And now you put the next layer in the spaces between the balls in the previous layer. Now, if you just have two layers, there's no, everything's equivalent. You just have two layers, you can rotate them, but there's no true degree of freedom. But when you add the third layer, if you remember, there are twice as many holes as there are circles. So basically, there are two options where to put the third layer. One of them is to align it with the first layer, and the other thing is something else. And these correspond to these two different lattice dimensions, so the HCP and the FCC. Okay, so this is about dimension 3. Now, dimension 4, 5, 6, and 7, unfortunately, to our shame, we mathematicians are not sure what is the optimal packing density, but in dimension 8, there is some miracle. So in dimension 8, there is a remarkable object called the E8 lattice, which is a highly symmetric lattice. And if you draw the spheres, the direction of the sphere is very tight. It's as tight as it is in the two-dimensional case, in the case of the hexagonal circle packing. In dimension 3, if you just look at the ball and its neighbors, it has 12 neighbors, but they're not completely tight. There is some room you cannot fit 13 balls, but you could put 12 balls, and okay, it's not a canonical arrangement. But in dimension 8 and dimension 2 also, you get a perfect kissing, so it's called perfect kissing of balls, meaning you have a canonical arrangement, everything is tight. And Blichfeld, in 1934, proved that among all lattice, not among all field packing, but only among all lattice field packing, it is optimal. And Marina Vyazovsky, in a breakthrough result for which she got the Fields Medal in 2016, she proved in dimension 8, this E8 lattice provides the best field packing among all field packings, not just among lattice field packings, which is the density is roughly 0.25. Okay, now in the time of Blichfeld, this field packing problem was a rather theoretical question for mathematicians. Who cares about 8 dimensions? I mean, it's nice from the point of view of quadratic forms and number theory, but it has no, I think, I'm not an expert, but I think it had no practical application at the time. But situation has changed in the 1940s and 1950s with the development of computers and communications and error correcting codes. So if you work on a Gaussian channel, you do digital coding, you need to code messages as vectors in RN that you're going to broadcast, and the models that Shannon introduced in 48 was one of them was the Gaussian channel, these are points in RN, and then you want to decipher your messages, then it makes sense to have the messages as far as possible from each other, and they measure noise in L2 sense, you want Euclidean distances, and this is one reason why there was a revival of interests in field packing starting from the 50s. Another source was that finite simple groups. So finite simple groups, the classification and should later, and some groups are similar to groups of lattices. This was another great source of development in this area. So beginning in 56, there was a period of focus on field packing, on also analogous problems where you do packing in a discrete cube, in the Hamming cube. And as part of this development, John Leach, in 1965, was very well versed in many subjects of mathematics, discovered another remarkable object in dimension 24 among all numbers. Okay, this is called the Leach lattice. It has again a perfect kissing, and it has a large symmetry group, which is an important group, the Munster group. And Vyazovsky, Radchenko, Miller, Kumar, and Kohn proved in 2017 that this is the optimal dimension 24. Okay. And the density of the field pack in dimension 24 turned out to be roughly 1 over 500, 0.002. In some sense, you can say it's a very small number, but you could also say it's, okay, on the other hand, it's the volume of the unit ball in 24 dimensions, okay? And I grew up, I do high dimensional geometry, dimensions which are really high, and in my mind, the n-dimensional unit ball is a tiny object, it's a tiny volume. Its volume is roughly 1 over root of n to the n. It decays much faster than 2 to the minus n. So when I looked at this thing, I was a bit surprised to see that in dimension 24, I get something which is much larger than 2 to the minus 24. 2 to the minus 24 is 1 over 16 million, not 1 over 500. But somehow, as it happens, the asymptoticity in the dimension takes time to materialize. So yeah, anyway, so that's why you could, so there's a reason to say it's a small number or to say it's a too large number, but this is the truth. So that's what's known about sphere packing in sphere dimensions. Now that's what's known about other things. So first of all, I should have said there are two notations that I'm using. There is delta and delta bar, okay? So what's the difference? Delta bar n is the optimal density of just some sphere packing in Rn. N is field packing, and delta n is a smaller number. I mean, okay, it's not larger at least, and that's the optimal density of a lattice field packing. So if I insist that my field packing would be a lattice field packing, I call it just delta n. Okay, so dimension 2, 3, 8, and 24, delta n equals delta bar n, but in general, delta bar n could be larger. Okay. Now let me tell you a simple bound for the optimal density of field packing in Rn. My claim is that if you make one possible way to do field packing in Rn, just to put balls in some arbitrary manner until there is no space left for an extra ball. This is what I call the greedy algorithm. Just put, and then you cannot do it anymore. My claim is that if you have this, apply this algorithm, you would get automatically a field packing with density at least 2 to the minus n. Okay, so this is the kind of basic construction in this business. Why is it true? Why would I get to the minus n at least? That's because of the following fact. So if I cannot, I have a collection of say unit balls, and I know that there is no space, disjoint, there is no space left for an extra ball. Okay, so this means that if I take any point in my space and I try to draw a ball around it, something is disturbing it, something is interfering with it. So this means that there is another ball of distance at most 1 from this point, or if you want, there is another center of distance at most 2. So this means that each point in Rn is of distance at most 2 from one of the centers. So this means that if I scale the balls by a factor of 2, they would cover all of space, the entire space. And when I scale by a factor of 2, I multiply volumes by 2 to the n. So this means that the original density was at most, so after I scale by 2 to the n, the density is at least 1, it means the original density was at least 2 to the minus n. Okay. So that's one lower bound for delta bar n. I have a table here with some, okay, that's what known about sphere parking. More is known about lattice sphere parking. It's an easier problem. And here the answer is known in dimension 4, 5, 6, 7. And recently, probably it was proven also in dimension 9 using computer simulation of billions of lattices. I think it was done in dimension 9. Okay, now, so we have this table, and actually there are more tables in some books. And physicists, Parisi and Zamponi, looked at these statistics and tried to make some conclusions. Actually, they did much more, I'll explain it later. And they looked, first of all, they said that it makes sense not to look just at the density delta n, but it makes sense to scale it by a factor of 2 to the n. That's what they said. And after you scale by 2 to the n, they thought that the graphs indicated it goes exponentially in dimension, but then they claim that they're not so sure it's really true, because maybe it's quite possible, they wrote, that this is a pre-asymptotic effect. So somehow it's hard to make predictions from statistics from low dimension about the behavior of delta n for large n. Okay, there is another reason to scale a little delta n by 2 to the n, and that's because after you scale it by factor of 2 to the n, it has a clear geometric meaning. In fact, let me call it capital delta n, 2 to the n times delta n, has a geometric meaning. My claim is that capital delta n, 2 to the n times delta n, is exactly the volume of the largest volume of an ellipsoid in Rn, which is centered at the origin, which does not contain any integers. Okay, let me try to draw it in a picture. So we have, this is, let's say that this is z to the n, what we have here. And our goal is to try to draw some ellipsoid. Let's say Euclidean ball is a type for an ellipsoid. I want to draw a Euclidean ball that avoids all integer points except for the origin. So the Euclidean ball is one contender for being an ellipsoid which is integer free, but there are also other possibilities. You can also take some other ellipsoid, like, I don't know, like, let me try to draw it, like this one maybe. This one is another example for an ellipsoid which is integer free, okay? And if you remember, in high dimensions, the unit ball is a tiny volume. I just said it. So the unit ball is indeed integer free, does not contain integers, but it's really not a strong contender in being an ellipsoid of maximal volume without any integers, okay? And you should believe that there are larger ellipsoids with largest volumes that do not contain any integer. However, it's pretty hard to find them. I mean, how would you find a good ellipsoid? So, how would you find a good ellipsoid of large volume which does not contain any integer vector? And it's not Euclidean ball. It's pretty hard to understand that. Even in dimension 2, 3, I mean, you get some specific ellipse, the image of the under some, but it's pretty hard to describe them. But there was a breakthrough in this problem by using probabilistic constructions. So Minkowski and Hlavka, at the end of the many years ago, at the end of the 19th century and also at the beginning of the 20th century, they were able to prove that there are such ellipsoids that avoid all integer vectors in any dimension whose volume is at least 2. Okay, 2 is already a reasonable number. It's not a very tiny number. The unit cube is volume 1. Okay, so we were able to find an ellipsoid that avoids all integer vectors except for the origin, center, whose volume is at least 2. But it is a random construct. I'll explain as you do it. I want to explain it a bit. It's really interesting. But nobody knows how to get something explicit. And in the year 2000, few mathematicians compiled a list of open problems in mathematics. There is such a list by the mathematician Peter Sarnak from Princeton. And in his list, I think it's problem number 10, is to find an explicit construction of an ellipsoid, which is integer free. Nobody knows how to describe in an explicit way such an ellipsoid. There is no precise definition of what explicit means, but it's something that when you see it, you recognize that explicit. Okay, so the problem of sphere packing is equivalent to the problem of finding an ellipsoid of large volume which avoids all integers. And I leave it as an exercise for you. You see the proof idea, but I leave it as an exercise for you to fill in the details and understand why it's the same problem. Okay, so Minkowski said that you can find an ellipsoid whose volume is at least 2. Then there was an improvement by Rogers in 1947, and Rogers proved that you can find such an ellipsoid whose volume is at least n times c, where c is a universal constant. In this lecture, when I say I write the letter c, I mean some explicit number. Okay, so Rogers was able to improve upon Minkowski model by a factor of n, by a linear factor. And the question that remains is what is this number c? And along the years, people had a lot of improvements and attempting proofs about this number c. So Rogers was 2 over e, then 1.67, then almost 2. Then Stephanie Vance got 6 over e, and she introduced a new method using quaternionic symmetry. Everything is non-constructive, as you understand. So nobody knows till today how to get an explicit ellipsoid, which is integer free, of sizable volume. Then Venkatesh proved a very large constant. It even showed better. It shows that in some dimensions, so lim sup means that in some dimensions, the density grows, you will get a factor of log n. You could say that log n is a tiny number because if you take log of the number of atoms in the universe, you get, I think, 6. It's not clear it's in practice it's a large thing, but it breaks this, psychological barrier, or it breaks this idea that really the answer should be linear. When I think it's super linear after this result, that's a very good thing. Now, Venkatesh not only proved the constant and broke this linear obstacle, he also made the conjecture. The conjecture was that this quantity, capital delta n, this quantity grows just polynomially with the n. So it should be like n squared, n cubed, maybe n, but not more than polynomially in the dimension. Okay, I will discuss I'll discuss what it means when I discuss upper bound. It means pretty much that if you look only on lattice field packings, in some sense we say that density 2 to the minus n is the trivial density. It's like almost this greedy algorithm. So basically, what this conjecture suggests is that all you can do is just a polynomial correction over this rather basic construction of 2 to the minus n. So there's no way, if the conjecture is true, there's no way to get exponential improvement by using lattice field packings. Okay, so that's a conjecture, but it's not proven. Next, what about non-lattice field packings? So it's for most of this problem existed for quite some time. Usually it's easier to describe lattice field packings, and it's just non-lattice are less accessible for mathematicians, but they're still out there, and people were able to produce non-lattice field packings, typically by doing a Poisson process, just throwing points randomly for the center of the circles, and then eliminating intersections and removing some such constructions. And Kivlevich and Vardy gave another proof of the Rogers bound at some point. Then the physicists Parisi and Zamponi, they got interested in this problem of sphere packing. And they used a certain non-rigorous method in physics, in statistical physics, called the replica method. So this is a highly successful method in statistical physics for which Parisi got the Nobel Prize 3-4 years ago. It's an important method in physics, but it's not completely rigorous method. Nevertheless, it gives good predictions in many cases. And in these years, 2008, 2010, they wrote papers, very cautious papers, they did not make a strong prediction, but they describe a scenario under which the density of sphere packing in Rn is roughly not that far from the Venkatesh conjecture, roughly n log n times 2 to the minus n. So this is, it's, I would not, you can, they wrote very, very careful formula. I mean, they did not commit themselves to this conjecture. It's not something they really believed in. They made many assumptions which were not clear for them that they are correct or not. And later in follow-up papers, they wrote that this is scenario, there are several scenarios, and this was scenario A. Scenario A was that it's n log n, then scenario B was a different polynomial, and scenario C was exponential. Just one of the scenarios. It's not a fully committed prediction. Nevertheless, some mathematicians were influenced by this prediction of the physicist, by this conjecture or speculation of the physicist. In Campos, Jensen, Michelin, and Sarasabuda in 2023, they managed they discussed this prediction by the physicist and managed to prove it up to a factor of 2. This is pretty much natural in mathematics. The methodology of mathematicians is much more demanding. We want to prove something. It's not enough to have some kind of speculative argument with some moves that are not entirely legitimate. So it happens in many cases that physicists make predictions and mathematicians prove them up to a factor of 2 or something slightly weaker. Another interesting thing is that in 2023, I think it was the first time in many years that the world record in sphere packing was not held by a lattice sphere packing. Okay. However, the lattices did strike back and last year we proved another bound. So we proved that capital delta n does not behave, is not n and not n log n, but much higher. So we proved that it is at least n squared. Okay. So this is in accordance with the Venkatesh conjecture. We have lattice field packing in Rn, density at least n squared times 2 to the minus n. And if you think about, okay, there is some reason to believe that this could be the correct polynomial. If you believe in, okay, first leap of faith, you should believe in the Venkatesh conjecture. And if you believe in the Venkatesh conjecture, there is another conjecture which says it should be n squared for some reason that I'll now explain. Okay, so this is the result that is new. Okay, now let me move to discuss upper bounds for sphere packing, and also I want to discuss a bit about this conjecture, whether you can have a dramatic exponential improvement or whether you only have polynomial improvement in high dimensions for sphere packings. I'm not completely sure. What's known about upper bounds for sphere packing? So first of all, there is a very nice and sweet paper from 1921 by Blichfeld. I think there is this post from the book by Paul Erdős. That's not far from that mid-level. It's really, really very sweet proof, in which Blichfeld gave an non-trivial upper bound for density of sphere packing, any sphere packing, not just lattice. So we know that, I mean, obviously, the density cannot be higher than 1. That's a trivial upper bound. And we have this lower bound 2 to the minus n. Okay, so what Blichfeld proved basically is the geometric average, 2 to the minus n over 2. So Blichfeld proved that the density of any sphere packing in n dimensions is at most 2 to the minus n minus 2 times a polynomial factor. And this is roughly, in high dimensions, 0.71 to the n. Then the exponent was improved in the 70s thanks to the development of a field called linear programming in the 30s, 40s during the Second World War, both in the US and in the Soviet Union. There were developments of field of mathematics called linear programming, which was very influential and very useful. And as part of this, it was also useful for these ideas were useful. Okay, you could say that Blichfeld is a precursor to that. But Kabiati and Yansky eventually improved better bound using a linear programming bound. But that's not known for today. So what we know today is that the upper bound is 0.66 to the n, the lower bound is 2 to the minus n times n squared, and there is a huge exponential gap between these two numbers, and we are not sure what is the truth. So I have no, I mean, personally, I don't have any belief at all about general sphere packings, but for lattice sphere packing, I do have some feeling for those. And let me tell you what okay, let me do some arguments about the question of exponential versus polynomial growth of the density of sphere packing of lattice sphere packing, only the lattice case. So what are the arguments that people have for exponential improvement over the known lower bound for capital delta N? So the first argument, I think I told you, statistics from low dimensions. Okay, but it seems okay. That's an argument. The graph seems to grow fast. However, some asymptotics tend to materialize. We saw that in dimension 24, the volume of the unit ball is too large. So I mean, many things in this business, I think you need hundreds of dimensions to be able to really understand what's going on. Another argument in favor of the exponential growth is that there are some algebraic constructions of lattices coming from some groups that are really too good to exist. They don't give you good sphere packing, but there are other problems like kissing number problem, and they're just too good. So I mean, if you apply the polynomial, the random philosophy, they would not exist. So the fact that they exist weakens this polynomial conjecture. Another argument in favor of the exponential growth is that there are some analogous problems for which we do have exponential improvements. Okay, the analogous if you take a finite field with q elements, q is at least 40 something, then you can get, there is analogous problem, and there you can have exponential improvement over the trivial thing. Okay, not in the Hamming cube, by the way, only for very large cube. So these are some arguments why you'd believe exponential growth. Why would you believe polynomial growth? So the idea is roughly, this is my belief, so I said, Venkatesh conjecture. Why does it make sense? So the idea is that if you look at the space of all lattices, the space of all lattices, it has, it's a non-compact space, I'll explain in a second. It has like a bulk and cusps. So there are lattices that are, let's say, mainstream lattices that are in the area where random lattice should behave. And there are more exotic lattices that are have a very short vector, they're almost degenerate. And it seems that the packing lattice should be roughly a random lattice, should belong to the bulk. These lattices are not the one, not the fringe lattices. The ones that are special are usually do not give you good packings. They have short vectors. And if it's a roughly random lattice, then you can pretty much say the following. I can just discretize my space. The space of lattices is dimension n squared roughly, so you should discretize it by using n to the n squared, e to the n squared log n points, okay, roughly. And you have e to the n squared log n points, which are kind of random. And for a random lattice, you have kind of a good understanding of what's going on. So you can say the probability that the random lattice will give you a packing of balls of volume R is roughly e to the minus R. So you have this number of experiments should succeed in this probability, blah, blah, you get a polynomial bound of n squared log n, actually. That's what you get from this Venkatesh heuristic. So that's some heuristics that will give you polynomial growth. Nobody knows what is the answer. Okay, so this is about this phenomenology of lattice sphere packings, and sphere packings in general. But this is lecture in mathematics, so I want to say something about proofs. Okay, I will not say, it will not be too technical, just a little bit technical. Okay, and there is one really nice proof that if you come up from this lecture and you just understand this proof, I really feel that I really did my job. And this is the Minkowski-Hrabka proof. Okay, so let me tell you a bit about the proof methods. How to get a good lattice sphere packing in Rn, how to find a good ellipsoid that avoid all integer points. The first step is to do some abstractization step and look on the space of all lattices of covolume 1 in Rn. Okay, we mathematicians like to group objects. This is starting from the early 20th century, Hilbert, things like that. So you have space of L2, space of functions, and function is now a point. Now we have a space where lattice is a point in the space. This is, if you know some mathematics, you are maybe used to this level of optimization. So we look at Xn, the space of all lattices of covolume 1. And this space is actually a smooth manifold of dimension n squared or n squared minus 1. Okay, it's a reasonably nice behaving space. However, it's what's called a non-compact space. So lattices can go to infinity. Okay, so you have the lattices can degenerate. You can have volume 1 by having very points very close to the origin. You can have the fundamental set going to infinity. So it has kind of ends, which are tentacles going away to infinity from this space, which is a bit annoying. Okay. Nevertheless, let's look at the positive part. It's a smooth manifold, and it is a homogeneous space. What does it mean, homogeneous space? Homogeneous space means that it's a space that looks the same at near each point. Or in other words, it has a very large group of symmetries. So R3, our space, is a homogeneous space. Why? Because you have a group of translations acting on it. You can have some region in space, and you have an isometry, a translation that maps a given point to any other given point. It's all kind of the same. That's why R3 is a homogeneous space. The same happens with lattices. So there's a transitive group action. If you take a lattice and apply a linear map determining 1 to 1, it would still be a lattice of the same covolume. And you can transform any lattice to any other lattice using such a transformation. So this is why it's called a homogeneous space. There is a group action that can transform each lattice to any other lattice and lots of symmetry, space which is highly symmetric. Now comes some developments of 19th century mathematics, and in particular there is something called the Haar measure. So whenever you have such a space, which is a homogeneous space, you have a transitive group action on such a manifold of finite dimension. There is a way to associate measure on this space, to measure volumes of this space. And what Minkowski and Zegel discovered is a totally remarkable object. They found that there is a probability measure on the space of lattices, which is canonical, which is invariant under the direction of the group. So this is something quite shocking. So this means that we can measure areas in the plane, everybody knows. We can measure volumes in space, also everybody knows. But the fact that you can have in the space of lattices a canonical, completely canonical notion of volumes that is invariant, a unique concept of probability invariant under all symmetries of the space, that's a semi-miracle in my opinion. And this means that we can generate lattice, so we can flip coins. It's a probability measure. Yeah? We can have a random lattice. You can flip coins and generate a random lattice in a way which is invariant under the group of symmetries, under linear expression determinant 1. Okay, that's okay. That just have in mind that you can sample a random lattice, and all lattices will be the same after you sample in the sense that if you take your space and stretch it by factor of 5 in some direction or factor of 1/5 in the other direction, stretch it in a volume preserving way, it will be the same law, the same distribution, even after this scaling. That's quite a remarkable property of the world, that there is a random concept of a random lattice, which is invariant under linear transformations. And there is a corollary, which is called the Ziegler summation formula. And that's the following corollary. So we have a notion of a random lattice. We're very happy with this notion. Now we can we can take some test function, and let's look at the sum of this test function over all non-zero lattice vectors. I don't know, maybe the function is just gives the value 1 if you're inside the ball and 0 outside. You just sum it over the lattice and take the expectation. It's a random variable, take the expectation. The miracle is that this complicated thing, sum over the lattice, take the expectation, equals to a very simple thing, to the integral of the function f over all of Rn. That's the miracle. And why is it kind of clear that it follows from the symmetries? Because if you think abstractly and you look at the left-hand side, there's a functional on the space of functions, on L1 in this case, you understand it has some invariances, and then you can characterize what are all of the invariant functionals on the space of functions, and basically the only possibility is the integral times some constant, and that's how you prove it. Just by these invariances, you get that there are very clean, beautiful formulas. Now let me try to prove for you the Minkowski-Clark compound. Okay, so we fix a Euclidean ball B, whose volume is slightly less than 1. Just a ball of value 0.99 in Rn. Okay? This ball is large radius, root of n. The volume is 1. The radius is large, right? The unit ball is small volume. So If the volume is 1, the radius is root of n, it's a large number. Now let's count how many lattice point non-zero you have in this ball. This is some integer number, non-negative. You take the expectation. You can write the expectation of what? So how do you count how many points are in this ball? You can look at the indicator function, 1 on the ball, 0 outside, and sum it over all non-zero lattices. And take the expectation. But the Ziegler summation formula tells us that this expectation is just the integral of the indicator, which is the volume of B, which is at most 1. At least strictly smaller than 1. Interesting. So what did we discover? We have the expectation of a non-negative integer valued random variable, which is strictly smaller than 1. So it means that this random variable, the number of points, cannot be always above 1. It has to be 0 somewhere. And if it's 0, we found a lattice that does not intersect this ball. This exactly gives you this ellipsoid that you wanted. So this is the proof of the Boaz-Klartag bound. It gives you 1. In the remaining 1 or okay, that's the main proof of this lecture. In the remaining 1 or 2 minutes, let me just explain to you how do you get the n and n squared. So you get the n by using something called the Minkowski second theorem with successive minima. This is what Rogers did. So you estimate something slightly more complicated, and then our idea to get the n squared was to start with some ellipsoid and let it evolve in the space of ellipsoids in the following way. The idea was to start with the ellipsoid and deform it continuously in the space of ellipsoid so that whenever it hits a non-zero lattice point, it keeps on its bound at all later times. Let me show you some graphics. I start with some Euclidean ball and let it evolve, and it keeps these green points on the boundary. But when it hits a new non-zero point from the lattice, it keeps on the boundary in the later evolution stages. Okay, that's the graphics. And in high dimensions, if you count degrees of freedom, you'd expect your ellipsoid to touch n squared boundary points in this evolution, which would be a random evolution, everything is random. And now there is some heuristic called the Poisson heuristic, the Poisson point heuristic, which says that you have 1 point per unit volume, and therefore you'd expect your ellipsoid to reach volume, which is the number of points, which is n squared. So that's why you'd expect your ellipsoid to reach volume of n squared when reaching once it gets n squared points on the boundary. So that's how we proved our n squared bound. Okay, so my 45 minutes are up. So I think I'll just stop here and thank you very much for your attention.
Okay, yeah, thank you very much for this talk. I now try to allow people to unmute themselves and turn on cameras. So I think now, if everything works, everybody can unmute yourself. Feel free to turn on cameras and you can ask questions. Also, there are a few questions in the chat. Boaz, if you can look at the chat now and start with answering questions from the chat, and then people will continue to ask questions.
Okay. Okay. Is there some duality notion between spheres and hexagon? Hexagon in this packing is called a Voronoi cell. In this case, at the end. Yeah. It's very So yes. So there is if you have a lattice in Rn, it is a fundamental domain, and you can look at the following. When you have a lattice, you can look at the following objects that Voronoi discussed. Bogdan said the Voronoi cell. The Voronoi cell is the collection of all points in your space, whose nearest lattice point is the origin. That's a cell, and the hexagon is the Voronoi cell of the hexagonal circle packing. In general, the Voronoi cell in Rn, in typical situations, it is a polytope whose number of facets is 2 to the n plus 1 minus 2. Okay, so in the plane, 2 to the n plus 1 minus 2 should be 6. And it works. Yeah, and in dimension 3 it's 12. Yeah, that's the Voronoi cell. That's the subgrid of delta cosmological dimension. Yes, that is dimension. Replica method is usually accurate. This is the first time I see it fails. Okay, I apologize. I'm not a physicist. Okay. And by the way, so I did correspond with Zamponi, and he also invited me to see them in some conference of physicists. And they started now a project of numerical simulations to understand what went wrong with the replica method. But it was not. Also, they were very careful in their papers. You can look at the papers of Parisi and Poni. Also, there they were kind of very, very cautious that what they do is not entirely legitimate. Okay. For D equals 2, the hexagonal circuit binding lattice is unique. Yeah. For dimension 3, it's 2 Kelvin. Yeah. No, in dimension 824, it's unique. 824, there's unique objects.
Okay, so I also have a question. So have you tried to actually implement your random process of this ellipsoid, evolving ellipsoid in dimensions like 4, 5, 6, 9, whatever?
The physicists, the physicists are doing it. Yes. So Francesco Zamponi, he corresponded with me and they started project of simulations. Yes, and in particular, they've tried this. So my code is called the evolving ellipsoid. I think that I hope they'll implement things like that.
Yeah, so I'm interested, what will be the first dimension when your construction, asymptotically, it beats everything. So we can do the simulations and then just find out what will be the smallest dimension when it beats everything, yeah.
I'm a theorist, I don't know. I do high dimensional geometry in the sense of dimension tends to infinity. This is my specialty. So I'm not an expert on it. I don't know if the dimension 50, 500, or 5 billion. I just have no idea. Zero idea.
Also, you have a constant small c in your theorem. Have you tried to estimate it exactly?
First of all, it's effective. So you could get some estimate. I did not optimize this constant. I hope there'll be follow-up works and people would optimize the constant. I also suspect there should be a log factor, by the way.
Mm-hmm.
I have a question.
At least it's interesting just to look at the optimal packings in low dimensions and see what is the best constant which works at least in all low dimensions, for which we know some constructions. So this will be kind of the upper bound for possible constant.
I agree. I completely agree with you.
Mm-hmm. Okay,
I have a
so
question.
maybe I'm asking too many questions, so other people, please join.
Yes. Very good question.
Yeah, anybody else? Do we have any questions?
I have a question. I have a question. Can you hear me?
Yeah.
Can you hear me? Okay, good. What about yeah, hi, Bob. Good to see you. Thank you for your talk. Yeah, nice to see you. What about in the sphere or in hyperbolic space?
That's a very different question. Just a different question, and I don't know. I mean, it's a natural question to ask how to pack balls in hyperbolic space. I don't know. There is some issue there. Okay, it's a different world completely. I don't see even the 2 to the minus n, even the trivial 2 to the minus n bound or bound. When you scale balls by a factor of 3 in the hyperbolic space, the volume is not just double. It doesn't double by some factor. It's uncontrolled, right? It's a very different problem. So
well, it's hard to define density even, right?
Another
hyperbolic
issue,
space.
Another issue is that it depends on the radius of the ball. So in Rn, I didn't have to mention the radius. I mean, it could take radius 1 or the same answer. In the hyperbolic space, I don't think it's the same. Well, maybe I'm not saying.
Okay, thank you.
I don't have like good dilations. It's a different question. Yeah, I mean, I don't know. Look at the sphere, for example. If you do a proportion, you can do the sphere, right? It's pretty much dual situation. On the sphere, it's you can take finitely many circles and try to pack them, and it depends on the radius of the circle. And it's a different world. I don't have much. It depends on. Okay, there is one extra parameter you should pay attention to, which is the radius of the ball you take. It's not the 2 parameters: dimension and number of balls. Dimension and radius of the balls. You should. It's a 2-parameter problem at least. Yeah.
Thank you.
There is also one question in the chat, new question. Can you see it?
Could you please recall why the results of Parisi were important for the community? I can open the paper. Should I do it? It is analogous to something that happens in the liquid phase. I'm afraid to. I will do injustice if I try to. I mean, I'm complete amateur in this physics thing. I just I can open the paper here in front of everybody and let you look. It's an ongoing subject. There are still, I mean, so papers coming up every few. I mean, it's a subject. The high dimensional packing in the physical, starting from Parisian point. Okay, they see some the phase transition that they see is analogous, most by means of analogy. Also in the book, there is a book by Parisi Zamponi and someone else about the replica method. There is a chapter on sphere packing in high dimensions. I'm afraid to. There is some materials in chemistry that are relevant. I'm afraid to say. I don't know. Sorry.
Okay, thank you. Any other questions?
How does the approach could improve real-world application like origami? It cannot. Sorry. I wish. I don't know. It's an abstract thing. Theoretical mathematics. I do not know how to. I mean, unless you do some project. I mean, you can think about projecting from high-dimensional space, like the tesseract or something like that, and having some. I mean, yeah, it requires imagination well beyond my abilities. I have no idea. I mean, I hope it gives inspiration to someone, but I'm not the person that I really know very few things. But yeah, sorry. Yeah, I don't know how to have origami.
Yes, it's obvious that if you have some nice constructions, more optimal in high dimensions, and then select a nice projections, you'll be some nice picture on the plane.
Yeah. You get nice picture on the plane, right? Yeah, but origami, wow. If someone can do it, please tell me. I'm being yeah. Yeah.
Yeah. Any other questions? Okay, if there are no other questions, then we'll thank the speaker for very nice talk. I will remind everyone that thank you everyone for coming. I will remind that the next talk in 2 weeks' time by Professor Avi Wittgerson. And so hope to see you all there. Yeah. So thank you.
Okay. Thank you. Bye-bye.